Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hey everyone. I am PS Chaturji with you, and I'm fired up to be back with your channel, Structural Design Only, a channel with different vision. Power of Shapes Part 2, Moment of Inertia, How Shapes Resist Twisting. Hey everyone, welcome back to the channel. In part 1 of our Power of Shapes series, we mastered the concept of mass center. Today, we're tackling a brand new challenge, moment of inertia or MOI. Ever wondered why a spinning pizza crust wobbles more than a basketball? It all comes down to MOI. This fascinating concept tells us how much effort it takes to change an object's spin, basically its resistance to twisting. Here's where things get exciting. In this video series, we'll specifically dive into calculating the MOI for squares, rectangles, circular, trapezoidal, isosceles triangles and even compound trapezoidal. Because we have to face this type of section in our daily structural engineering life. In this video I am going to demonstrate MOI for squares, rectangles, and isosceles triangles. By the end, you'll have a deeper understanding of how shapes behave when rotated, opening doors to solve real-world engineering problems. But wait, there's more. If you're curious about applying MOI in practical scenarios, or if you simply want to see some mind-blowing spinning object demonstrations, then stick around for the entire video. Don't forget to smash that like button and subscribe to the channel for more awesome structural engineering adventures. Concept of mass and moment of inertia or MOI. The moment of inertia is a property of an object that describes its resistance to rotational acceleration. In simpler terms, it's a measure of how difficult it is to spin the object around a particular axis. Traditionally, moment of inertia is calculated using the total mass of an object and its radius of gyration. But what if the object has a uniform density and thickness throughout? In that case, for thin plates or sheets, we can actually use the area of the plate instead of the entire mass for moment of inertia calculations. There's a catch, though. To get the correct moment of inertia, you need to multiply the area by the density of the material and the thickness of the plate. So, remember, moment of inertia usually depends on how the mass is distributed, but for special cases like thin, uniform plates, area can be a helpful substitute. The moment of inertia is related to the mass and radius of gyration of an object. In fact, it can be expressed as the product of the mass and the square of the radius of gyration. Now the question is, what is radius of gyration? The radius of gyration is a concept that represents the average distance of all the mass elements in an object from the axis of rotation. It's a hypothetical distance that allows us to treat the entire object's mass as if it were concentrated at that specific distance. Here letter small r represents the radius of gyration. In this picture you are watching a plane area divided into 6 segments. This are segment 1 to segment 6. Say we know the area of each segment, and they are A1 to A6. Say we also know the radius of gyration of each segment from a fixed line, that we called axis of rotation, and this distances are R1 to R6. We can express the moment of inertia of the section about this axis as sum of A1 into R1 square to a6 into r6 square. Up next, we'll explore how the moment of inertia of square and rectangular section. Moment of inertia of square or rectangular section. Alright, let's kick things off with the humble square or rectangle. The moment of inertia, MOI, of a square or rectangular section about an axis passing through its center, this center we also called centroid, can be calculated using this formula. Say, segment area equals to A, at a distance x, from x-axis. Consider a small weight of the segment, dx. Therefore segment area, A equals to B into dx. Say, moment of inertia of the segments equals to A into x square for top segment and A into minus x square for bottom. Total of this 2 equals to 2 into A into x square. Now total moment of inertia of the section about x axis equals to 2 into B into integration of x square, with lower limit 0 and upper limit d by 2. Therefore Ixx, of the whole section, equals to 1 by 12, into B, into d cube. Similarly, Izz, of the whole section, equals to 1 by 12, into d, into b cube. Where b is the length of the square or rectangle and d is the depth of the square or rectangle. Before we move on, it's important to remember that this formula assumes uniform mass distribution throughout the square. Key takeaway from this portio is, the more mass an object has further away from the axis of rotation, the higher its moment of inertia. Up next, we'll explore how the moment of inertia of isosceles triangle. Moment of inertia of isosceles triangle section about base. This slide shows how can we derive the formula for the moment of inertia of a isosceles triangle section about its base. Base length of this triangle is b and height, h. Consider, an infinitely small section have a length pq, and at a distance x from apex of the triangle and thickness dx. Rate of change of horizontal length at the rate of b minus 0 by h equals to b by h. Therefore length pq equals to b into x by h. Say area of the strip equals to a, and a equals to pq into dx equals to b into x into dx by h. Therefore moment of inertia of the yellow hatched area, about base of the triangle, I base equals to a into r square, where r equals to h minus x. Finally we have the moment of inertia of the strip about the base of the triangle, I base, equals to a into whole square of h minus x, equals to b into x by h into whole square of h minus x into dx. Now to get the moment of inertia of the whole section, we have to integrate the above equation and we have to consider lower limit as 0, and upper limit as h, and say this is IBC. After doing that, we are getting an equation, IBC equals to 1/12 into bh cube. And this is our equation of moment of inertia of the whole isosceles triangle. In the next slide we are going to know the theorem of parallel axes. The parallel axis theorem. The image illustrates the parallel axis theorem, which is a principle used to calculate the moment of inertia of a planar lamina or flat plate about an axis that is parallel to, but offset from, its center of gravity, cg. The theorem states that the moment of inertia, IBC, of the area about an axis, BC, parallel to the first axis through the center of gravity, g, and at a distance d from the center of gravity and total area of the section, a, can be found by using the following formula. IBC equals to IGXX plus A, into D square. Or, IGXX equals to IBC minus A, into D square. Where, IGXX, is the moment of inertia of the triangle, about axis parallel to the base BC and it is passing through the CG of the triangle. To find the moment of inertia of isosceles triangle section about the XX axis, in the next slide we are going to apply the theorem of parallel axes. In our previous slide, we came to know that how we can calculate the moment of inertia of an isosceles triangle, about its base. Now I am going to demonstrate how we can find the moment of inertia of this triangle, when the x-axis of this triangle is passing through the CG. To do that, we have to take the help of parallel axis theorem. Already we know, moment of inertia of isosceles triangle section about its base equals to IBC equals to B into h cubed by 12. From the parallel axis theorem, we know that IBC equals to IGXX plus total area into r square, or we can write IGXX equals to IBC minus total area into r square. Where IGXX is the moment of inertia of this triangle about XX axis through CG and r is the perpendicular distance between base and this axis passing through CG, and value of r equals to h by 3, where h is the height of the triangle. Say total area of the triangle, A. Now we know A equals to B into h by 2. Therefore we can write IGXX equals to B into h cubed by 12 minus B into h by 2 into square of h by 3. Finally we have IGXX equals to B into h cubed by 36. Now we have achieved our first goal. In our next slide, our target is to find the moment of inertia of this isosceles triangle, around ZZ axis passing through CG. In our previous slide, we found the moment of inertia of an isosceles triangle, about its XX axis passing through its CG and parallel to its base, IGXX equals to B into h cubed by 36. Once again by the help of the parallel axis theorem, we can write IZZ equals IXX plus A into D square. Since isosceles triangles are bilaterally symmetrical about z-axis, its CG will remain on the z-axis passing through the CG distance form z-axis will be 0. So the value of D equals to 0. Therefore value of A into D square equals to 0. Finally we have IGXX equals to IGZZ equals to B into h cubed by 36. Now I am switching over to Excel spreadsheet. Now we are watching the value of B equals to 3 and value of D equals to 3, then moment of inertia the square section around XX axis, IXX, equals to 6.75 and around ZZ axis, IZZ equals to 6.75. An unit of this moment of inertia will be length to the power 4. For an example, if we consider the length unit as meter, then unit of moment of inertia will be meter to the power 4. Now I am changing the values, say b equals to 4, after changing the value of b, we are getting some warning, and below the cells ixx and izz, there are no results. Because we know, for a square section, b must be equal to d, so I am also changing the value of d from 3 to 4. Now on the display board we are finding the values, moment of inertia, the square section around xx axis, ixx, and izz changed from 6.75 to 21.333. We are also watching the formula of moment of inertia below this results. Now I am changing the shape from square to rectangular. Once again, we are getting some warning, and below the cells ixx and izz, there are no results. Because we know, for a rectangular section, b and d cannot have same value. Here the value of b equals to 4 and value of d equals to 4, so we have to change one of this value. Say I am changing the value of b from 4 to 5. Now we are getting values of ixx and izz, and moment of inertia, the rectangular section around xx axis, ixx, equals to 26.667, and around zz axis, izz equals to 41.667. Now I am changing the shape from rectangular to isosceles triangle section. Once again, here the value of base, b equals to 5, and value of height, h equals to 4, so no problem. Now we are getting the values of ixx and izz, and moment of inertia, the rectangular section around xx axis, ixx, equals to 8.889, and around zz axis, izz equals to 8.889, and below this value you are watching the formulas.
Hey everyone, thanks for watching. Before we wrap up, I wants to talk about something important for the future of this channel. As you know, the channel focuses on civil and structural engineering topics, which can be quite niche. While the content is valuable for engineers, it might not be the most engaging for everyone. Here's where you, my fellow engineers, come in. This channel is approaching 3,500 subscribers, which is fantastic. However, watch time is lagging behind. If you're an engineer and find this content valuable, please consider liking the video, subscribing to the channel, and leaving a comment below. Your engagement helps the channel grow and allows me to keep creating content specifically for you. Together, we can build a strong community for civil and structural engineers on YouTube. Till then, bye bye, and see you next time.